So welcome everybody to this first lecture of the Jedi Academy. So I'm going to start with a quick introduction here about why we are doing Jedi. What's the whole point of this project. So first of all, just a few words about what the Joint Center for Satellite Data Assimilation is. So we are a multi-agency center that was created in 2001 to improve the use of satellite data for predicting weather, ocean, climate, and the environment. And the agencies that are involved in the JCSDA are NOAA for several of the NOAA branches of the National Weather Service, NESDIS, and OER. NASA through GMAO is also a partner, as well as the Navy and the Air Force. And the idea really here is to share everything that's common between these agencies to better use satellite data. So there's a lot of work that's taking place when satellites are launched to create even new CRTM coefficients, new operators, new QC, all that. So the idea is to share all that between these government agencies. And the way we are organized is by project. So one of the longest running project is CRTM, Commodity Additive Transfer Model. You will hear about that a little bit when you look at the UFO later in the week. And the other big project, which is more recent, is Jedi, the Joint Effort for Data Assimilation Integration, and that's what you will hear about a lot this week. And we have a few other projects that kind of came with Jedi, and one is SOCA, so it's the Sea Ice Ocean Coupled Assimilation, which is using Jedi for doing ocean data assimilation. What we call the OBS project, which is about the use of observations in general, and LAND, which is for land data assimilation. And there will be potentially a few other projects, for example, about the atmospheric composition that will be coming in the future. And really the idea here is that when the JCSDA was created in the year 2000, the focus was really on the increasing number of sounders for radiances and how to use them for operational NWP. That was the initial focus. In the 2010s, there was a lot of focus about improving the usage of the radiances for NWP. So that included things like all sky, all surface radiance utilization, this kind of things. And now in the 2020, we are moving into the next step, which is to use the radiances in coupled data assimilation and in applications other than just the atmosphere. And that's where the Jedi project really came to start. So we are just really taking a proactive approach here to future data assimilation challenges, but the overall mission of the JCSDA hasn't changed in that whole period. It's still to make better use of satellite data and share the work and reduce the duplication of work between the agencies as much as possible as we go. So now that I've gave this brief introduction to the JCSDA, I'm going to talk a little bit more about Jedi, why we started this project and what this is about. So first of all, sorry, Jedi is a joint effort. So I've put here a list of some of the names that have contributed. The list is actually longer than that, and it's growing all the time. So we are centered around a core team who are really JCSDA staff. And then we have in-kind contributors from all the agencies that are involved in the JCSDA. Plus a few others, like for example, NCAR is also participating with the members of the JCSDA, as well as the Met Office, for example, in the UK is also now a part of a Jedi project. And we've had quite a few academies already. So this is the 6th academies. We've had 5 before. So we have a fairly a significant number of people now are starting to use Jedi. So the objective of Jedi, as I mentioned, as for the rest of JCSDA, is to reduce the duplication of effort between the partners. So it should be easy for any partner to add new observations through UFO and Yoda, which you will hear a lot about this week. So I'm not going to really go in details now. But the idea is that if a partner adds an observation into this UFO and Yoda, then all the other partners can also use it. And this way, we can put together a much bigger workforce to collect and a full list of observations that we want to use, and have the largest collection of observation operators and observations that we can use in any data simulation system if we collectively work on this. So that was already an objective of a JCSDA, but we made it much easier with UFO and Yoda, which are part of Jedi, and we also extended that to conventional observations. So the UFO and Yoda also include conventional observations, so it's more than just satellite. And another change with Jedi is that the same is now true for data simulation algorithms. So we have a component of Jedi that's called OOPS, which I will explain in a minute. That if any of the partners adds new data simulation algorithms in OOPS, then they should also be usable by all the partners straight out of the box. And that's, so we've kind of extended a little bit what we mean by use of observation to include the data simulation. Another driving idea behind Jedi is that we want to bring all the components of the Earth system into one data simulation system. And the idea is to then move to coupled data simulation. So if we can do the atmospheric data simulation as well as the ocean and land surface and etc. in the same framework, in the same system, then it should be much easier to then move to coupled data simulation progressively. And that's one of the big ideas that was behind the design of OOPS, which I will go back to in a minute. Finally, another objective of Jedi is to bring together research and operations and to develop a system that's used for both, so that there is a very easy transition between research and operations and vice versa, so that people doing research can reproduce an operational system in order to study it and improve it. And when somebody doing research has a new developments that can be used for operations, then they can easily be transferred because it's all based on the same system. So that's also one of the ideas behind Jedi. Another idea that was at the base of the system is that modern data simulation systems are really too complex for one person to understand entirely. They have too many components, too many different areas of science that are involved, from computer science to math to physics to knowledge of the observations. It's not possible for one person to understand everything. So we need collaborative developments. And if we want that to work, we need to be able to use what's called separation of concern, where one person can work on their area of expertise without breaking what other people might be doing in other parts of the system. Now, this complexity, this level of complexity is not something that's unique to data simulation. If you look at the world around you, and in particular all the software today that's used from your smartphone to your computers, your GPS, all the tools you're using now in everyday life are extremely complex pieces of software. Nevertheless, they move very quickly and they work. Compared to 20 or 30 years ago, software is a lot more reliable than it was. So we want to make use of all these techniques that have developed in the software industry and apply them to our system. So we've taken an approach to use modern software technologies. So that includes programming technologies that would help develop software faster, make maintenance easier, and increase the portability and efficiency of the whole system. So we'll go back a little bit into this. So let me start a little bit with OOPS. OOPS stands for Object-Oriented Prediction System. That's a project that was started at ECMWF a few years ago. And the idea there was that all data assimilation algorithms, if you read the scientific literature, they are based on a few entities that are a model state and a model and some covariances and some observations and a few others. But it's a fairly limited set of entities that are used to describe the algorithms, to explain them, in a paper. And what the idea with OOPS was that the code should look like the papers, really. And we want these various operators and entities that you see in the scientific literature, like the X and Y and H and M and B. We want those to be visible in the code. So we've defined these interfaces, which are the green boxes here, the state, model, covariance, etc. And we've defined interfaces for these classes, and we've written our data assimilation algorithms and high-level algorithms in general that are in blue at the top, using these interfaces. And then on the other side, below the green boxes, you have these kind of reddish boxes where we actually implement these various elements. So that gives us a clear boundary between the what we call like the high-level algorithms and the actual implementations that are below. Now that's all based on object-oriented and generic programming. So even though the name is object-oriented prediction system, it's actually the generic programming aspect that's a more important one here. But GPS didn't sound as good, and it was already taken, so OOPS was better. And the idea here is separation of concerns. The whole design of these interfaces was driven by the idea of separation of concerns. How can we separate so that somebody working on the model can make a change in the model? It's not going to break the data assimilation. Somebody working on the covariance can make changes there and improvements, and it's not going to break the model, and etc. So that's they're clear interfaces, and there are no global variables. That's another major change for people who are used to old codes. Everything is passed through interfaces. And that's one way of ensuring that you're not going to change something that's going to break something else, because you see clearly from your interfaces what is used where. So that's OOPS. And now going into Jedi. So Jedi is a little bit more than just OOPS. So OOPS would be the blue box at the top here. That was on the previous slide. And in Jedi, we've added a generic layer to OOPS. So there are things here like UFO and Yoda. So these are actually implementations of some of the green boxes. So the observation operators in particular, where we've implemented them in what we call the UFO. And that UFO, which might then call things like CRTM and ROPP or operators for GNSSRO, etc. The idea is that these generic implementations can be used with any of the models. So we don't need to re-implement the OOPS operators for each model. So the very first version of OOPS, you could develop a new data assimilation algorithm like a 4D var, and it would work with all the models, but each model had to implement its OOPS operators and all the green boxes. Now we are moving one step further, and we implement the observation operator only once for all the models. And we've also added another component, which is called Saber, which is for the background error covariance matrix, which again is being made generic and can be used with all the models. So there's less and less that people who want to put a new model in the system have to do, and then they can use all these generic components that we've added. So I'm going to go just I have one slide about model interfaces. This is a schematic of how Jedi interacts with the models that are in Jedi. So typically when you have a model, you have some setup at the beginning, then you have a loop over time steps, and then at the end you have some kind of cleanup, sometimes not. So really we've interfaced at that level. So what OOPS and Jedi see are they call these two methods. So we split the setup into two parts, the create and initialize. The idea there is if you want to run your model several times in the same executable, create is called only once, and initialize will be called at the beginning of each model run. So whatever needs to be repeated, you put in initialize. What you don't want to repeat, you put in create. Same with finalize and destruct. And we also have this step function that we can call, and that will advance the model by a certain amount of time. Now, this is not exactly just a time step of a model. We don't actually need to see what's a time step. Really, what we call a step here is we have this idea of a time resolution. So it's how often you want to see the state of your model as the model is advancing. So a step is really that. It's really defining what you can see as a time resolution when you're dealing with your advancing the state. And the idea really here is that between the steps we can do whatever we need for the data assimilation. So which is typically going to be comparison with observations. So this h of x, this obs operator. But there can be a few other things like initialization, like a digital filter, or a few other things. And we call this what we do during this model run post processors. And it is just a generalized idea of what a post processor is. The idea is that these post processors, they do not modify the state ever, so they do not impact the forecast, and that's a very important point here. And this way we have a good separation of concerns between the model, that's what's happening inside these three blue boxes, and everything else, which is not directly related to the model advances, and that we should be able to modify and do anything we need without changing the model. So there's a separation of concern here between the models and the DA, and actually if any other high-level algorithm that we need to use and call the model. So that I guess is answering the questions we had earlier. This is a list of the models that are currently interfaced with Jedi. The list is growing. I think it's complete at the moment, but there might be more. So that gives you, there's a majority of atmospheric models, but not only. We also have some ocean and sea ice. And we also have what we call toy models, that are very simple models that people can use for academic studies. And we are really planning to use these simplified models for teaching data assimilation. I think there's a big need there for teaching data assimilation, and we can use those and still do it in Jedi, which is a good way to teach both data assimilation and Jedi for future generations of scientists. I'm going to, again, going quickly in the observation interfaces. So as I said at the beginning, the driving idea behind GCSDA was to reduce the duplication of work when it comes to using satellite observations. So we've kind of moved forward a little bit and extended that in Jedi. And we've taken the model agnostic approach one level more into the obs operator. The idea there is that we can share the work and accelerate the work to use new observations. So if you think about regular satellite missions, they're very expensive. You don't want a satellite to be up for 6 months before you can use it. That's tens, if not hundreds of millions of dollars that are wasted. We also more and more are seeing CubeSat that have very short lifetime. If it takes you a year to start using it, then chances are that this CubeSat will be down before you start using it. And also, if we give a common interface that can be used by all the partner agencies, it's much easier to get the instrument science team to get involved in the development of these observators, because they know that if they get involved with the JCSDA and with the UFO, then all these agencies will be able to use their work and their instruments and their observations. So there's a bigger incentive there for these teams to be involved. So we've developed what we call the UFO, Unified Forward Operator, and the idea is to build like a community app store where you can download your favorite operator and use it with your system very easily. So that's the picture here is representing what's commonly, how observation operators commonly work in current data simulation systems. You have an observation operator, and it goes and it taps into the state of a model and accesses directly into the state to find whatever inputs it needs. And then from that, it generates observations, which again are in a data structure that the ops operator goes directly into. And the boundaries between the state, the ops operator, the observations are a bit blurred. And more, even more importantly, it's very tied to a given state, so to a given model, and there's no way you can take an ops operator and use it with a model other than the one it was developed for. So what we've done instead in Jedi and UFO is to put some clear boundaries between the state and the ops operator. So an observation operator needs, from the state, it needs the value of certain variables at certain locations. So the ops operator will pass to the state the locations and the variables that it wants. There is a method in the state that's going to either, if the variables are already available, it's going to just return them, or it's going to get these variables somehow and compute them and return them in what we call field values at locations here, which is a well-defined data structure where the state is going to copy the values that the ops operator needs, and the ops operator can then continue and simulate the observation. So these classes that are in gray here in the middle are well defined, and they can be easily shared. And the only thing that when you put a new model into the system is you need to implement that one function or method that takes as an input the locations and the variables and returns them in this specified data structure. So once you have that, all the observation operators can be easily exchanged and compared, and there's all kinds of science you can do with that. So that's really applying this idea of separation of concerns, and that everybody is passed through the interface through these three gray classes that are there, and not through some global variable that would go and be hidden, and that the ops operator would start going into some of the model internal structures and to get what it needs. Then we have this idea of filters that come with the UFO. So these are filters can be called before or after the ops operator, and the idea really started with doing the QC, quality control. They can actually do a few more things, and you will hear a lot more about that tomorrow. So I'm not going to go into many details here. The main message here is that these filters are generic. So once you write a filter, it's entirely controlled from a YAML file, and you can use it with any model, any observation type, and define, for example, your background check. It's ops minus h of x. And if it exceeds a certain threshold, you can reject your ops or do something, take some action, inflate the ops error, whatever. really the idea, the message here is that it's generic. If there is a background check or a thinning that you want to use, you don't need to rewrite it. These filters exist, you just reuse them. And that's the message here. We already have, I forgot, there's more than 20 filters, I think, at the moment, and more will be developed as needed. Of course, there are a few filters that are fairly specific, and that wouldn't really make sense with some of the observation types, but overall, it's fairly generic. So, and this is just an example. You will see a lot more about that tomorrow, about the validation of the UFO and the filters that we are able to reproduce exactly the GSI quality control for AppsUA using generic filters. So using completely new code, we've been able to reproduce exactly the quality control, which was something that was a big question mark at the beginning, that many people thought we would not be able to do that. And actually, quite a few people thought we would not even be able to get close to what the GSI was doing, but we can reproduce it exactly. There's absolutely no problem there. And this is another example here of using the quality control, the filters in an ocean data simulation application. And these are filters that were developed for the atmospheric data simulation. And they've been reused in an ocean context without any coding, just by changing the configuration. You see a background check here that has a threshold. So of course they change the thresholds to be what they need, but and a bounce check and things like that. All these filters are completely generic. They've been reused in Ocean DA without coding. So that I think is a big success of this whole approach of the UFO and the filters, and it is really what we wanted to see, and so it's great that it works. Okay, observation handling. I'm not going to say too much here, but you know that typical data flow for observations are fairly complicated in operational systems, and there's all kinds of files that have been converted and used and then converted some more to go to the next step, etc. So we've developed this interface for observation data access, YODA. And the idea is that we have only one interface across the whole chain. As soon as data arrives, it's converted into this this format, and then there is one interface that's used for pre-processing, for monitoring, for plots, and for the data simulation itself. And it's also ideally the same interface for the entire memory hierarchy, so going from you know, in memory to disk and archive. And it's also available from C++, from Python, and from Fortran. So that's again, to simplify the work of the scientist here. The scientist should see that one interface, and they shouldn't have to worry about how the data is stored below that interface. Again, separation of concern between computer scientists who would worry about the data structures and the scientists who would do really their science and just use that interface. So a few words now about the working practices. We have obviously many people, many organizations, many models, and we are making fairly fast progress. So this project started about 3.5 years ago, and we have a lot of things working already. So progress has been much faster than in development of any data simulation system. So we've the methodology we use is inspired by Agile Scrum type of method. We had to adapt a little bit to distributed teams and many part-time members of the team. But the idea really is that we work in small, manageable increments with constant feedback. So there's every time a small piece of work is done, it's merged into the code base, and there's feedback, there's code reviews, etc., so that we constantly learn and improve. We have a modern collaborative environment where the source code is easy to access for GitHub. We have an easy way to discuss the code and discuss the issues, discuss what's being done for ZenHub. We work for pull requests and code reviews, where hopefully all the developers are actually actively involved. So every time a small piece of work is done, there's a pull request, the code is reviewed, and then is merged into the main code base. And really the idea is that this pull request should be small. So nobody should work for 6 months or a year on something and then merge it. The unit, if you want, that we're working with is much, much smaller. It should be a few days of work. Sometimes can be a week or two, but really nobody should work on their code for much longer than that without merging. That's the idea there. We have a lot of meetings using video, and we also have code sprints where the idea is to put a few developers together in the same room to work on a very specific topics and really be able to discuss in depth one specific topic. And so these code sprints are really that. They are really people coding. And when we invite people for a code sprint, they come with their laptop and with the code, and we code together. And it's not a workshop or a committee or just discussions. It's for coding. Obviously, this year it has been remote. We've not been able to do that with the people in the same room, but hopefully we'll get back to that very soon. So this is just a schematic of all the repositories we have in GitHub. I'm not going to go into detail. You will learn more about that this week, but the idea there is that it's separation of concern. So each specific piece of code is in its own repository, and we don't have one giant monolithic code that has everything, and where people, the code is so intertwined that people have to know everything before they can do anything. So that really you should be able to work on separate pieces independently or fairly independently. There's still a few exceptions when we change the interfaces, but that is happening less and less, hopefully, now that we're converging. Just a few more things about the infrastructure and working practices. We have automated testing and enforcing of the coding norms. So on every pull request, we'll trigger these tests, and you will see the result of the tests. And we cannot merge a pull request if it's breaking any of the tests. And that's why we also encourage you, when you develop a new feature, to put a test that goes with it, because if you don't have a test, then your feature might be broken because people don't know that they've broken it. So it's important every time you develop code to develop a test to go with it. It ensures that your code is correct, and it ensures that it will not be broken in the future. We're also making a big effort on portability. So we have a fairly flexible build system, and all these tests are run automatically with several compilers, so we're sure that the code stays portable at every step along the way. And it's not, we want to move away from that idea that operational centers should work on one machine. They develop their code for that machine, and then when they get a new machine after a few years, they have to spend a year porting it to the new machine. That is really something we don't want to do in the future. And because we develop code that has to work for several partners, it has to be portable anyway. And we also have a lot of documentation that you will see this week, hopefully. So Jedi Academies, this is the sixth academy. Unfortunately, because this is remote, you're not going to get your lightsaber at the end, which is a shame, but in spirit, it's there. A few examples about the code sprints, which we try to keep fun. So final comment. As I said, collaborative work is a constraint, but it's also, I think, a very motivating, very interesting, and you learn a lot more than you would working on your own. It does require an effort in doing code reviews, and hopefully people can do that quickly. The other thing is that what we want to mention is that the fact that code is in the code base doesn't mean that it's used in operations. There are lots of options in the code, lots of different ways you can use it. And then it's up to operational centers to decide what they want to use in all the code that we are putting in common here. So there's several steps. There's technical developments. Once that's done, the code can be merged in, and with some very basic checks that it's not breaking anything. Then there's a scientific evaluation, then there's a move to operations. And each step would fit back into the previous one for this kind of agile way of working. And I think I'm going to stop here because I've said all the things that are on this slide already before, but the idea really is that we are working in science, but that's not a reason to not use modern software development technologies, and we shouldn't be stuck with methodologies from past centuries, in terms of software development, and we should make use of object-oriented programming, generic programming. Are technologies that have been in use for more than 20 years, and they are reliable and they work, and they make the software you use in your everyday life much more reliable, much more easy to modify and adapt and evolve, and we should really use that. We shouldn't be stuck in the past.